Hello, everyone. My name is TorinJ, and today I will be presenting on a paper called On Non-Cooperative Location Privacy, a Game-Theoretic Analysis. It's written by these lovely individuals, and I'm not going to try to pronounce their names because I might get it wrong, and presented by yours truly. Now imagine you're walking just down the street. You have your phone on you, and it's sending and receiving data. Your identity is generally secure, but someone is able to follow the pings of your phone, and in doing so, see what locations you go to. After a while of tracing your location, the adversary knows who you are. That's the core problem this paper is based upon. But really, this is a multi-layered problem, and it initially starts with authentication in mobile networks. So the mobile network requires authentication from whatever device is on it, the different nodes. Public keys are sent to verify the identity, and the public keys can be monitored to find the location changes. And it's really tough to change this initial verification technique. So instead, focus could be put on location privacy for mobile nodes. That's kind of the second problem. Instead of just one public key and one pseudonym, there could be multiple given, a full set, and these change over time. However, this requires coordination of neighboring nodes so that they can change at the same time. So then the next question goes, how do we coordinate the nodes? Synchronous change is really difficult. That's the same place at the same time, and it almost never occurs. We could make it so that there's base station coordination, but this relies heavily on infrastructure, and so that can be pretty difficult. There's also something that's called a predetermined mix zone, but that really lacks flexibility and requires prior knowledge as to where and when these mix zones occur within a network. Next came broadcasted mix zones. So this ends up having more flexibility because it's based on a mobile node broadcasting its want for change to neighbors. This seems like a pretty good solution. However, there is high overhead, which reduces network performance, and there's only assigned a limited number of pseudonyms per node, so it can be costly to change frequently due to the scarcity. The number of zones traversed must also be small to remove limitations imposed on mobile users. This is because when a node changes its pseudonym with all the other nodes as well, it has to go into a silent mode for a little bit, where it's not able to receive or transmit data or messages to other nodes around. And as such, it's possible that this could impose something on the actual user because the phone is not receiving service for that brief moment. In addition, selfish nodes who don't participate in the zones could actually cause a low location privacy guarantee. So if all of the different nodes are in this mix zone, and a lot of them end up not changing their pseudonym, then it doesn't actually help out in the end. And that's really the goal of this paper, to investigate whether the multiple pseudonym approach achieves location privacy in non-cooperative scenarios. And that's really where game theory can be used as well. If some nodes are willing to cooperate and some aren't, well, what are the specifications as to when one will cooperate and when one won't? After giving this problem framing, the authors then go into some prior research and related work. This is mainly on threat analysis and then different identification techniques. In threat analysis, using other papers, it was shown that it's easy to identify individuals based on where they go, especially when you're using something like cars, which can find homes and therefore find identity pretty easily. For different identification techniques, they looked at physical ones, such as MAC changes or fingerprint changes, which are almost more on the infrastructure level. And they also looked at group signatures, ring signatures, and anonymous credential systems. These are all different methods and different ways to provide additional security in pseudonym changes. However, none of them seem to work quite as well as doing the mix zones. Lastly, they also looked into some papers that looked into game theory analysis on security as a whole. This was different than what their goal was, but it just showcased that game theory can be used within this kind of a context. Next, the authors talked more about how they modeled the system for their analysis. The base of this model is a network of autonomous entities that communicate wirelessly, such as vehicles or phones. There is also an offline certificate authority which pre-establishes the device credentials, and this occurs outside of the model parameters themselves. Prior to the network entry, every node registers with the certificate authority and receives a set of the public-private key pairs. This also uses a discrete time system as the nodes move through the system. These nodes are automatically exchanging information as they go, and they advertise their presence periodically to the other nodes around. Legitimacy of the nodes are controlled through the certificate checks using the sent public key. As part of the model, they talk about the threat. The aim of the adversary is to track the location of the mobile nodes. This is given that they have the same credentials as the mobile nodes and eavesdropping communication tools. These could be anywhere from an individual to a global adversary, someone with a lot of access in the network. They collect the pseudonyms, and based off these pseudonyms of the other nodes, they can create location traces. But as part of the model as well, they cannot alter the key pair generation of distribution, so that's something that's outside of their reach. Now, as with the main problem statement, The main focus of the model is with multiple pseudonyms. This is on the coordinating of pseudonym changes within mix zones. The adversary then would have to predict the likeliness of a new pseudonym and an old pseudonym being linked to continue location tracking, which would be pretty difficult to do, and is why that was the main focus. So in the model itself then, each node is able to evaluate the potential distance it's been tracked by an adversary since its last change of pseudonym. It uses the knowledge to decide when it should change its pseudonym again, and then it's able to send a request to other nodes within the proximity when its privacy level is lower than desired, or it's under the assumption that it's been tracked by an adversary for quite some time. Other nodes may choose to participate or not then. The below graph represents the idea of this model, where beta, the y-axis, represents the privacy loss function. T1 represents the first confusion point, or mix zone, where the pseudonym change occurs. Over time, we get to a point TF, which represents the final time before location privacy is assumed to be too low, and another confusion point, or mix zone, must be reached. T2 is when that point occurs. We must also take into account how long that should last given a successful confusion point in which more than one node changed their pseudonyms. This is given through A of Ti, and this has bounds of 0 to log 2 of n, all of which is shown within the actual model itself when the game theory approach is taken. That being said, let's look into this game-theoretic approach, achieving location privacy in a selfish environment. As with many game theory approaches, the pseudonym game change has costs. So we have to consider the costs and the potential location privacy gain when making a pseudonym change decision. There are 3 costs accounted for. This is the name change itself with scarce resources, so acquiring a new pseudonym. This is the routing table updates, which can be costly, and the service access loss to communication when in a silent mix zone, so this is the cost to the user themselves. These are all expressed in something called privacy units, and rational nodes might not change their pseudonym based upon these costs. These costs make more sense when we look at the entire game overview. The authors decided to look at it as a static game, as they're silent mix zones, so there's no communication between the nodes at the moment that they have to decide whether or not they should change their pseudonym. There are 3 different components to the game. There are the players, the strategies, and the payoff functions themselves. Games can be played in parallel because you could have multiple mix zones occurring at one time, although they would be unaware of each other. The players are the nodes in the range of transmission to one another. In regards to the strategies, there are only 2, to cooperate or to defect, as a node can either decide to change its pseudonym as well, or to stay the same due to costs. And that leads us to the payoff function. This is based on location privacy gained versus the costs associated. There is one other thing that has to be taken into account with these games as well. Although not a main component, there's something called player types. This is based on probability density function, and more or less tells the information about the node's payoff for changing pseudonyms right before the opportunity. So all nodes know what every node's payoff is and can use that prior knowledge. This is mainly important within the complete information game, which segues us into the analysis of the complete information game. The authors decided to initially start with a 2-player game, as that was easier to look into. Now with the complete information game, this means that the nodes all know what the potential payoff function is for all the other nodes involved in the game. If we look at Theorem 1, which is an important result from the analysis of the game, we can see that the 2-player pseudonym change C game, or complete information game, has 2 pure strategy Nash equilibria. This is CC and DD, which is for both nodes to cooperate or for both nodes to defect, and 1 mixed strategy Nash equilibrium, which is based upon the probability with the cost and the payoff changing. This is the probability of cooperation of PI. So again, to reiterate, in total there are 3 NEs, 2 pure and 1 mixed. However, it was also found that to cooperate was the most likely Nash equilibrium. In addition, the game was asymmetric, and this is due to the probability changing between the different nodes as to whether or not they would cooperate or not cooperate. Now, if we look at the resulting table of the 2-player C game, we can see that CC consists of 1 minus gamma. Gamma is the cost of the pseudonym change itself. So if 1 minus gamma is a higher payoff than the prior payoff without changing, which is u to the minus to show that it was prior to the opportunity of the game, then both of the players would want to change because it's worth it in comparison to their prior payoff. If the prior payoff is better than the cost of the pseudonym change, then both players are going to want to stay with that. And then you can also have mixed occurrences when we change what the actual cost of the pseudonym change is. From here, we can go into the author's analyses of the complete information game when it's an n-player game instead of a 2-player game. This has 1 and at most 2 Nash equilibriums. The 1 is the all-defect strategy, where all the nodes decide that their prior payoff is better than one they would get with changing their pseudonyms. The second is possible depending on the payoffs of the involved nodes. For example, consider that there's 3 players going on in this game, and that the payoff of player 1 and player 2 is less than log 2 minus the cost before playing. Then, if we have CCD, which is player 1 and player 2 cooperating and player 3 not cooperating, that would become a Nash equilibrium, as every single time player 1 and player 2 would want to cooperate and player 3, which decides its prior payoff is better, would not want to cooperate. However, not every game has a Nash equilibrium with cooperation. With this being said, pseudonym changes only occur when, first of all, it's necessary, so there's low location privacy for the nodes, and when the other nodes are also cooperating. That wraps up the complete information game analysis and brings us to the more complex one, which is the incomplete information analysis. Before we get into that though, there's a few more additions to the incomplete game. First of all, it's quite a bit more complicated. There's a probability threshold that it's based around. If it is above the threshold, then defect. Else, the node should cooperate. This is based upon the location privacy bounds, where 0 is the lower bound, p is where the threshold is, and that's less than or equal to log 2 of n being the amount of nodes that are participating. A prettier way to show it is with the below function, where f theta is the probability of cooperation, and the probability of theta I has to be less than or equal to tilde theta I is the probability of the location privacy needing to be less than or equal to the threshold value in order for cooperation to occur. Now that we've established those additions, let's go ahead and look at the analysis of the incomplete information game. But just to start, we'll look at the 2-player game before getting into an n-player game, similar to our complete information analysis. Theorem 3, which the authors show, states that the 2-player pseudonym change I game has all cooperate and all defect pure strategy Bayesian Nash equilibrium, and every threshold equilibrium S equal to theta 1 and theta 2 is symmetric for continuous type distributions. Now, a few things about this. First of all, it has all the cooperate and all of the defect pure strategy Bayesian Nash equilibriums because it can represent any combination of nodes. And then as far as type distributions go, this is again based upon the probability distribution of a node's information and its probability as to whether or not it needs to change based upon how long it's been since the last time it's had a pseudonym change. Now, to continue this analysis and get to that theorem, the authors used a system of equations which used cumulative probability distribution and the cost. And they came out with this fancy looking equation. When they solved that equation, they were able to find that the threshold value had in its existence gamma, which again is the cost, and 1 minus gamma, with 1 minus gamma being all the cooperation solutions. When doing further analysis on this, it was seen that players should cooperate more when the pseudonym cost is higher. The authors didn't stop here though. No, they continued their analysis with over 1,000 simulations that they ran. This was through MATLAB. With these simulations, they looked at the welfare of the system, which is the average achieved utility, the fraction of interactions where pseudonym changes actually occurred, and the fraction of successful coordination between the nodes. This is where cooperation occurred. The results were similar to the mathematical analysis. When the cost of changing names increased, the cooperation also increased. These graphs represent further analysis, including probability distribution of user types, threshold, and probability of cooperation at the equilibrium as a function of gamma for different distributions of different types. There are 3 in total. For each type distribution, there are 3 BNEs. 1 coordinates to all defection, 1 to all cooperation, and 1 is an intermediate equilibrium. Again, as the cost of gamma of changing pseudonyms increases, these different BNEs changed as well. Theta 2 approaches theta 1, which means that the probability of cooperation actually increases. That wraps it up for our incomplete information game with 2 players, so let's go ahead and look at n players. Overall, it was pretty similar. However, now the authors had to consider the probability that k nodes participate and the probability of each cooperating. This results in symmetric equilibrium as well as cooperation via E existing only above certain values of gamma, which to them was really only anything above 0.3. For the main result, well, in summary, even with incomplete information, it is possible to find an equilibrium that achieves high location privacy and reduces the number of used pseudonyms. Here are some graphical representations of some of the analysis they did, looking at the threshold value at the equilibrium as a function of n, which is the number of nodes, for different values of gamma and distributions of 3 different types. For each type distribution, the number of B and E changes depending on the cost of gamma, similar to the conclusion that was stated previously. That concludes the game theory analyses on this specific problem and really has some pretty good results. But the authors decided they wanted to do one more additional thing on top of this analysis, and that was to create their own protocol, the pseudogame protocol. It takes into account the cost of changing pseudonyms and the probability of neighbors cooperating, in addition to other general features of nodes within a mobile network. This is based on the results of the n-player incomplete game, and it uses default understandings of node speed and really was made to assist nodes in choosing BNE strategies, again based upon the incomplete game analysis. I'm not going to walk us through all of this, but this is the pseudocode that they wrote for their protocol to give a direct representation. And with that, I'd like to bring us to our conclusion on this node location privacy and game theory paper. As a whole, the authors really are one step to further understanding non-cooperative behavior in location privacy schemes, and seem to have made a pretty great leap in the direction of better location-based privacy protocol, as well as a great analysis that shows that even with selfish nodes, there can still be location privacy resultants from these mixed zones. Now before we end today, there's a quick quiz. How many NE were found when analyzing the 2-player complete information game? Was it 2, 3, 5, or none? The answer can be found up above, somewhere in the presentation. I'm not going to tell you where, because you got to go and look and watch the presentation. If you did watch it, well then thank you very much for watching, and I hope you have a fantastic rest of your day.